Right. Good morning, everyone. Welcome to the Access Distinguished Lecture Series seminar. It will be delivered today by Professor Zygmunt Haas. It's my sheer pleasure to have him with us today. Let me give you in 3 lines a little bit about his background. He got his PhD from Stanford, then he moved on to Bell Labs, where he stayed for a number of years, and then he got a position as a member of faculty at Cornell University, where he still is a professor emeritus, but at the same time, he's a distinguished chair at University of Texas at Dallas. He's an IEEE fellow. He has a wide gamut of contributions, very significant ones in networking. He's, let's say, one of his claims to fame comes from being a pioneer in the area of mobile ad hoc networks before the turn of the century, and for many years, an area which is very important still nowadays. But let me not keep the stage any longer. Professor Haas, thank you very much for being with us. The floor is yours.
Thank you, Professor Papadimitriatos. Well, good morning, ladies and gentlemen. Thank you very much for inviting me here. I would like to thank Professor Zander, Professor Carlson, and everyone else who made my visit here possible. It's a true pleasure to be here to present some of our work. Just before I start with the actual talk, let me give a quick plug into my lab, which currently, as Professor Papadimitriatos said, is being hosted in the University of Texas at Dallas. I have right now 3 PhD students, 2 postdocs, and a number of undergrad master students. Most of my sources of funding come from National Science Foundation. I have some current funding from DoD agencies, as well as the University of Texas at Dallas. I'm going to go very briefly through some of the projects that we have been, recent projects that we have been working on in my lab. It's quite a long list, and I would say spans very, very different areas and maybe quite diverse areas. Of course, there's no way that I'm going to cover all of those projects today, so I chose to talk about one area, one particular topic, which is physical layer security, as you guys are going to hear in a moment. What somewhat distinguishes this physical layer security work that we have been doing from most of my other projects in my career is that I always have been known as a networking guy. And physical layer security, of course, is on the physical layer. My work has been progressing over time towards more the interface between networking and communication issues, in a physical layer in particular, and this is how you see this particular topic that have been addressed in my lab. The recurring elements in my work are collaborative behavior of nodes and entities, energy efficiency, loose network-wide synchronization of devices and nodes, secure and reliable operation in the presence of uncertainty, and finally, exploiting stochastic characteristic of the wireless channels. So this is a very, very high-level outline of this work today. One comment, maybe before I start, is to say that it's always a tough job to prepare a talk which is where the audience is relatively diverse in their knowledge and level of interest in the particular topic. If you are targeting the people who are expert in the field, of course, you're going to make all the rest people much less interested in your talk, and vice versa. My approach here was to present certain models in our work, which, as you are going to see, are simplified. And those models are made especially for the purpose of this presentation, so it will be easier for me to convince you of a particular conclusions that I want you to be convinced of. If you want to get a more extensive and in-depth treatment of those models, there are papers which are being referenced throughout my presentation, and there clearly much more extensive work is being discussed. The topic of today's presentation circles around the notion of reconfigurable distributed MIMO systems, and emphasis here is on the reconfigurable. The notion, of course, of being able to leverage from the collaborative communication through dynamic clusters formation. We're going to look at some aspects of such a technology or such architecture of networks, which I am a true believer that this kind of architecture would indeed be technology transferred to industrial partners and those people who are really implementing such systems. The second topic, which of course is related to the first one, is the use of this collaborative environment with dynamic cluster configuration for the purpose of providing physical layer security. And again, we are going to visit a number of topics here that relate to this aspect of the work. So let's start with the configurable distributed MIMO. It's a reference here of a paper, one of our first papers on this topic that includes more information. So the motivation for this work is that you have small footprint devices which typically have limited spatial diversity. The big idea of the MIMO, of course, is that the channels that you would like to have that are received over the multiplicity of the antennas should be as uncorrelated as possible. However, in small devices, the antennas typically would see correlated propagation channels. So the question is, can we use spatial diversity on a larger scale to be able to improve or reduce the correlation among those correlated channels? Some of the works on which we built our own research is the distributed MIMO, which is composed of uncorrelated multiple stationary antenna elements with large spatial resolution. And those architectures that are referred to as distributed MIMO leverage from the reduced correlation among the MIMO streams by spatial distribution. MIMO in cellular systems have several different, go under several different names: distributed antenna systems, coordinated multiport transmissions. Maybe the unifying element of those technologies is that they have typically stationary systems. In other words, there's distribution of antennas in the system for reduction of correlation among the MIMO streams. However, the aspect there which is more emphasized is the stationarity of those systems. We, in our work, are looking at dynamic systems in which the creation of those distributed antennas are through multiplicity of devices which are mobile. I want also to mention, which probably I should have at the beginning of my presentation, that I have a lot of material and limited time. So I'm going to skip some material as I go through those slides. I am, of course, always welcome to answer any questions that you may have. And I promise you that the material that I skip will not going to affect the clarity of the presentation, of the rest of the presentation. There have been works in which the cooperative and virtual MIMO are created by wireless sensor devices and mobile devices. There's clearly similarities with our model to a large degree. The difference is that in such works that are in the literature, multiple concurrent data streams are sent to form the cooperative MIMO from a cluster of nodes. This is in contrast to our proposed work, in which the assisting nodes are only recruited to improve the performance of a data stream initiated by the cluster head. So this will become even clearer when I talk about my model. But again, the idea is, so to speak, that I am a node. There are all these nodes around me, which can help me with my communication. And I would like to recruit those nodes temporarily for a very limited time, as long as I am in the proximity of those nodes, to assist me with creating a MIMO system. The application of such architectures are to, especially in the area of mobile-to-mobile communication, such as device-to-device, vehicular-to-vehicular system, IoTs, and so on. Application to cellular systems is also possible as well, but mostly in our modeling, we are concentrating on the mobile-to-mobile aspect. In our architectures, as you are going to see in a moment, we have two relatively distant nodes, which we refer to as cluster heads, with the desire to communicate over a channel which has insufficient capacity. Distributed antenna is formed by those mobile devices, again, by temporarily recruiting them to create clusters of much more powerful and higher capacity links. And the cooperative signaling is exchanged wirelessly within the cluster. So this is a little bit more in-depth, so to speak, presentation of our architecture. You have a transmit and the receive antenna arrays, which are formed by temporarily distributed nodes, which form those clusters. And those cluster heads, which really want to communicate between themselves, temporarily recruit nodes in their vicinity to serve their clusters. The intra-cluster communication is via local high-speed reliable connections. I can talk much more about this, and we are going to talk about it a little bit later in the second part of the talk. But essentially, the idea is that the communication within the cluster is by another type of technology, which is already has good performance because the distances are very small, and the inter-cluster communication is where most of the improvement is targeted at. Depending on the channel conditions between the nodes in both of the clusters, a subset of the transmit nodes are activated at each time for optimal performance and reduced overhead. As you're going to see in a moment, there's a trade-off between the number of nodes that I recruit from each one of the clusters. So if I'm a transmit head node, I have all those nodes around me, I actually should choose from those nodes a subset of nodes that's going to best help me to reach the destination cluster. And to serve this MIMO link, the clusters are periodically and continuously reconfigured according to some node mobility pattern and node selection criteria, which we are going to talk a little bit later in a moment. The frequency of the configuration is really a trade-off between complexity and performance. On one hand, as we are going to see again in a moment, you would like to select at any point in time the best subset of nodes that's going to best help you in achieving the highest capacity between those clusters. On the other hand, if you do it too frequently, you're going to incur a large overhead of signaling. So just here a trade-off, of course, how much reconfiguration you want to do. Clearly, as you can see here, on the issue of the configuration, which relates to mobility, this is where the networking aspect comes into play. Some of the contributions of the work that we are going to briefly discuss here is the ergodic capacity and the outage rates of such a system, and how often to determine how often the clusters have to reconfigure in order to best serve those nodes. So again, the reconfiguration rate is an issue, but also the choice of the nodes from among possible nodes in your vicinity is another aspect of this work. Okay, so this is my model. Again, I warn you, it's a very simplistic model for the purpose of the presentation. Our papers have a much more extensive model, if you wish. Here you have this transmit cluster in which you have a head node, which is in the middle of the cluster. In this case, the cluster size is of S. It's a circle of size S, and it's of distance d from a receive cluster, which for simplifying reason is described here only as a square. In order to tackle this mathematically, which actually presents some challenges, we decided to approximate our circular cluster by a square cluster of a square of size S. This approximation is being justified later throughout our work, showing that the error is very small. The assumption is that you have k transmit nodes that form the cluster itself. Those are the potential available nodes to assist me as a cluster head in my communication. Out of those k nodes, I am going again to select only a subset. The head node is responsible to encoding the information symbols into transmit symbols, a little bit more about it in a moment, and distribute the encoded signals to the corresponding assisting nodes. It's also responsible to synchronize the transmission or transmissions within the cluster. Please note that, again, all this, any communication between nodes within the cluster and the cluster head is over this high capacity, presumably reliable link, again because of shorter distances, significantly shorter distances than the intercluster distances. Similarly, on the receiving cluster, you have n nodes that form the cooperative receiving cluster, where the receive head nodes collects the signals from its assisting nodes and decodes the receive symbols. I want to, already from the beginning, to emphasize that the function of the receive cluster is more, as we are used to this term, amplify and forward, and not, I'm sorry, let me correct this, the function of the receive cluster nodes, not the cluster head. The function of the receive cluster nodes is to operate as amplify and forward, and not really and decode and forward. In other words, the decoding of the receive symbols is done at the head nodes, at the receive head nodes. This is the, again, simplified, very simplistic mathematical model. I present those equations and those formulas more for the completeness of the presentation. We don't have, of course, luxury here because of time limitations to go into very great depth in understanding the intricacies of this model. But essentially, you have long-term attenuation and short-term fading of the signal, of course, noise. And the assumption of the topology is that the intercluster distance, this d, is much larger than the dimension of the cluster, which was marked before as S. And therefore, we can simplify the multiplication of the path loss matrix with the Rayleigh fading matrix rather than being a multiplication of entry by entry to simply a matrix multiplication. The assumption on the signal model is that the large-scale fading, the shadowing, is ignored. So you saw again, for the purpose again of simplification, that there's no shadowing in my model. There's only attenuation due to distance and an attenuation due to fast fading. The assumption is that the path loss varies slowly and the compared to the fast fading, and over the coding block interval, the path loss is assumed to be constant. The fast fading remains constant over each coherent period, and the head nodes in the transmit-receive cluster encodes and decodes the transceive signal. The channel state information are being measured by the nodes. In other words, in an actual operation of the system, each one of the nodes in the transmit cluster is able to measure the channel between this node and every node in the receive cluster. How is it done? Well, we can talk quite a lot about this, but essentially any scheme which is able to sound the channel, such as schemes which are used in LTE and similar schemes, are possible. Another way to measure the channel by the transmit nodes is actually that the receive nodes will measure the channel and feedback the information back to the transmit nodes. Alternatively, the transmit nodes can simply sense the channel due to a reciprocity of the channels in both directions. We said that the intercluster transmissions are the bottleneck, and this is what we are going to concentrate while the transmit and receive signal within the cluster is being presumably to be very reliable over technologies such as Wi-Fi. Okay, mobility models, how the nodes are moving. So of course you can assume many different mobility models. In this work, and I'm going to show you some results in a moment, why we use these two mobility models. One mobility model is the Brownian motion. Of course, people do not walk as Brownian motion particles, but as we are going to see, the Brownian motion is probably one of the worst cases, so to speak, in the mobility. In other words, typically the mobility of users is much less random, so to speak, than Brownian motion models would portray. Over a period of delta t, the changes in the displacement of nodes is a complex normal random variables with some variance which depends on the diffusion coefficient. Another model that we use in our work is the random walk, which is based on constant velocity but random direction, and there the absolute value of the displacement is constant, which is the walk step. So this is a much less random model in the sense that the displacement is constant over the delta t period. We, of course, can define the velocity for such a model, which is simply this displacement divided by the step in time. Okay, so the first question that we would like to answer is the transmit node selection. We would like to have a practical node selection and reconfiguration scheme that utilize the path losses between the transmit and the receive clusters. Ideally, at any time, the subset of nodes that we chose for transmission to serve as a transmit cluster has the least or the smallest path losses. Of course, again, as we said before, this is only ideally. In practical situations, we somehow cannot achieve it, and we need to allow some degradation in performance, at which time we will then reconfigure the system to again improve the performance. The trade-off here is between the reduction in the signaling overhead associated with reconfiguration of the cluster and higher rates. So the operation, if you wish, of the system is, or the procedure for the node selection is that the transmit head node determines the maximum size of the cluster from system configuration. So this would be the absolute largest number of nodes that the cluster head would be able to recruit from. The system consideration could be the coverage area of the local links, the distance over which such Wi-Fi links, for example, operate, node density, fading characteristics of such channels, and so on. And the head nodes then transmits a beacon to this candidate assisting nodes to trigger the path loss measurement. The time averaged measurements are then sent to the head nodes by local links. As I mentioned before, the channel measurements could be done in a scheme, using a scheme similar to LT channel sounding. The channel measurements then can be determined either via the inverse link relying on the channel reciprocity or through the feedback from the received nodes. The transmit head node then activates L out of those K nodes. So K, again, is the total size of the cluster. L is the number of selected nodes. So if you were to order the average channel gains of the nodes, we will get some ordering in such a way that this ELF node has the smallest gain. In active nodes, the K minus L nodes remain muted, while the active nodes are allocated power by the head node. In this, our model here, we assume that there's equal allocation of power to all the nodes. Of course, this is clearly suboptimal. Nodes which see a better link should be presumably allocated more power. In some of our papers, we do present schemes how to optimize the selection of the power for such for those nodes. However, even in the cases of simplified models, such schemes for power allocation, optimal power allocation, are quite complicated. So one could, for example, assume that it makes sense to reduce the complexity of the scheme, to make sense to use a heuristic, and one of those heuristics would be an equal power allocation. of course, equal power allocation would make sense where most of the gains are similar. Small number of nodes, the selection of the small number of nodes, L nodes, reduces the power consumption of those schemes and therefore, of course, improves the interference, and signaling overhead are reduced by the channel measurements which are being conveyed within the cluster. In general, more nodes do not lead to better performance in this scheme. I'm going to try to convince you in a moment. Why is it so? Again, in this particular model that I present here, typically more nodes do not generally lead to better performance. And then there is an optimization step which will tell us how many nodes we should recruit. Using our, again, relatively simple model for the transmit of the L signals now, so now our K, our full system has been reduced to L system, so you have all those metrics reduced in size. Solving this, of course, it's relatively simple. Using regular MIMO systems will give us the capacity or Shannon rate of the per cluster node of the system. I'm not going to justify this. This is quite basic in terms of MIMO system. So we're not going to spend too much time on this. It is clear that the performance of the system will depend on the number of active nodes, L, that needs to be optimized. The achievable rate is depends on the fast fading and the path loss metrics, which are of course both random and could be averaged over node placement, which we refer to as typical node placement, which will give us the ergodic rate over the distribution of the nodes. The graphs that I'm going to show you to convince you of certain performance gains of such a scheme is going to assume that the L over N is being varied, but both L and N are being varied, but we are typically looking at the asymptotic behavior. So both large number of nodes are being selected in the transmit cluster, and large number of nodes being selected in the receive cluster. For such a regime, which we call asymptotic regime, we can receive, or we can simplify the achievable rate as being relatively simple limit with some equations that need to be solved to actually see the limit of convergence of this rate. I'm of course not going to go through those equations. There's no way that time will allow me to do so, but derivation of this rate is included in much more details in our paper. So this is one of the graphs that I want to present to you to convince you of how those schemes work. This is the average achievable rate as a percentage of active nodes, K of L over K, the fraction of the transmit cluster that you selected. Clearly, as you see here, especially for large K, there's degradation when L is large. So increasing L will actually reduce the performance of the system. And you can actually think why this is so. Because in our model, when you do so, you when you choose large L, there will be presumably large spread of those nodes, and a large spread of the quality of those nodes and the channel gains of those nodes to the destination cluster. And therefore, by choosing too many nodes, you're also going to effectively also choose poorer nodes as well. And it doesn't make sense to increase the cluster so much that you are forced to choose from the poorer nodes as well. This graph was made for the signal-to-noise ratio relatively high, so we call it the high SNR regime. The low SNR regime is very similar to this. What makes it a little bit even more interesting is the optimal number of nodes, which is the peak of those curves. I'm sorry, the L over K at which those peaks over peaks of the particular K at the particular K occur. As you can see, that the range of those L over K is relatively small. So the optimum for L between 3 and 6, as you can see, is the optimum is between 3 and 6, even for very large K, very large clusters. So you can have very large clusters, but from these very large clusters, actually only a small number of nodes needs to be selected to get the maximum performance of those schemes. This is for this graph is for low SNR regime, which is minus 10 dB SNR. Of course, if you think about it, this is probably the more interesting regime that you want your performance to be improved at. Okay, I'm going to skip this slide, just simply saying that the idea here is to show that if you don't want to select nodes, and you're going to select all the nodes in your cluster, meaning that L is equal to K, just for the purpose of reducing signaling in your cluster, for example, and or not being forced to make the measurements of the channels. Really, the increasing the K will not buy you that much. And there is some saturation here that occurs at particular K. So at K equals 8, you probably gain already most of the gain of your scheme, so to speak, and further increasing the or densifying the clusters do not lead to better performance. Briefly, with respect to node reselection, the idea is to understand how often I need to trigger the node reselection algorithm. And essentially the idea is to find the distribution of the time of this reselection time in such a way that if I were to reselect the node every tau, I will, in probability epsilon, I will be forced to truly reconfigure my cluster. So in other words, if I were to wait very long to reconfigure my cluster, the performance of my system is going to degrade. And I would like to know what is the reasonable time for me to trigger the system to the head node to start reconfiguration. Essentially, the idea is to say that in percentage of those times that I wake the cluster to reconfigure, this percentage of the time is truly the lead to the events in which reconfiguration is necessary. There is a better selection of the nodes than the nodes that are currently being selected. So if I am not so concerned with the optimality of the cluster, then I will make epsilon larger, right? So when I wake large percentage of the time, I will already be in suboptimal conditions. This will, of course, increase tau. Then the system will have less signaling and less frequent reconfiguration. On the other hand, if I want the system to always operate close to its capacity, I will choose epsilon to be small, and therefore tau will be small as well, forcing me to wake up very often and test whether the system needs to be reconfigured. We have a formula for the reconfiguration time for our Brownian motion model, and this is an approximation of this formula T epsilon. And as you can see, the complexity, trying to understand the complexity of this reconfiguration time and the amount of information that need to be signaled within the cluster for the reconfiguration. The time itself between reconfigurations is on the order of 1/k square, k being the number of nodes in the cluster, in the transmit cluster. And during each reconfiguration, you will collect O of k, feedback from those nodes, k nodes, that are going to convey their measurements to the head node. This could be reduced using what's called opportunistic reporting to O of k. Opportunistic reporting is a simpler scheme in which a node will report to the head node of a cluster only when its gain is above some level. So therefore, the total channel feedback per unit time scales as k square log k. If this is high, if you have a high k and you want to reduce it, you can use schemes such as randomly pre-select some number of nodes and sort of sample those nodes randomly for their gain. So this is with respect to the complexity of the configuration. Okay, some numerical results to show how it behaves at low velocities. The reselection needs to be performed in our model approximately every 3 seconds for small number of available nodes. In the case of larger velocity, this goes to a few tenths of about 10 or few tenths of milliseconds, depending on the value of k. What is really interesting in this model, of course, you can see that as the velocity increases, the reselection time goes down, as it should be. And as the number of nodes increases in the cluster, the configuration time also goes down, as it should. The interesting thing here is to compare the Brownian motion model with the random walk model, and you can see that the Brownian motion model is the lower bound for the random walk model. Without any proof and somewhat of a assumption, so to speak, or as a conclusion without proof, we believe that the Brownian motion model is truly very close to the performance of any mobility model. Okay, really very briefly, we present this reconfigurable MIMO to improve the spectral efficiency of small footprint devices, and we showed that the cluster reselection, cluster node selection, not only reduces the operational overhead, but also improves the performance. In other words, this L, judiciously selecting the L not only reduces the overhead, the signaling overhead, but also actually improves the performance of the system. Okay, we are going to, again, due to time limitation, going to skip to the second part of the talk. I know I probably wasted already 3/4 of my time, so it's somewhat, we have to go a little bit fast here. But I want to convince you of another point in this talk, and this has to do with using reconfigurable distributed MIMO for improving secure spectral efficiency. I'm going to very briefly state that physical layer security, which has been, of course, a very active area of research in the recent years, allows to relies on security which is very basic, which do not rely on exchanging of keys or any other cryptographic schemes. And therefore, a lot of people see the physical layer security as a stronger way, or if you wish, better. I hate to use the word better, but another strong way to provide security which would eliminate some of the concerns that we have with cryptographic security. Especially, this is especially true when you take into consideration that there are technologies, disruptive technologies, such as, for example, quantum computing, which give a lot of power to eavesdropper, to malicious nodes that can, for example, mount security attack by using extremely high computational power, and therefore, for example, do a very strong statistical analysis of data and so on. So the use of the RD-MIMO for to secure communication comes from increasing the number of the cluster member, and therefore I'll diversify the channel conditions. We're going to explain it in a moment a little bit more in depth. It also allows me to increase the SNR of the link that I want to communicate my confidential information over. It can leverage from node mobility and adjust the function of the nodes by additional functions such as artificial signal noise injection. Okay, this is a very basic explanation of physical layer security, just for the purpose of this talk. The idea essentially is very simple. I'm Alice, and Professor Papadimitratos is Bob, just for the purpose of this presentation. And we want to communicate securely, and there's one of you who is an eavesdropper. I want to be able to communicate with my destination in such a way that the eavesdropper is going to hear everything that I'm saying and will not be able to understand a single word that I'm saying, yet the destination will be able to understand everything that I'm saying. How is it possible? Well, the physical layer security original papers show that this is possible if the channel between me and my destination has some advantage over the channel between me and the eavesdropper. Advantage could be, for example, the SNR between me and my destination is a little bit better or better than the channel between me and the eavesdropper. The secrecy rate achieved over such a channel is the difference between the Shannon rates of the channel, of the confidential channel between me and the destination, and the channel between me, the transmitter, and a possible eavesdropper. So if there is some advantage of in the channel between Alice and Bob, positive secrecy rate is possible. The spatial mobility and diversity of the RD-MIMO, as well as the mobility of the nodes, allows us to improve the security of our communication, the secrecy rate. Why so? Because it allows me to create a better channel between me and the destination at the expense of the channel to the eavesdropper. Important things in our work, we assume that that Eve, the presence of Eve, can be in limited locations, but the channel information to Eve is not available. This is in contrast with a lot of work which have been published in the literature, which assumes the knowledge of Eve, the knowledge of the channel to Eve at the transmit cluster. Of course, such an assumption is not extremely practical because an eavesdropper can remain silent. The model for this physical layer security in the RD-MIMO is very similar to the model of the RD-MIMO. So I'm going, in the interest of time, I'm going to skip it and go directly to the optimization of the rate. The idea is that you want to maximize this difference between those two rates of the channel between Alice and Bob and the channel between Alice and the eavesdropper, subject to some power constraints. So really the optimization is over the power that you allocate to the various streams of the MIMO channel. Okay, the other aspect of this is to be able to select the nodes in such a way that I can maximize this secrecy rate. The selection of those nodes for maximization of the secrecy rate is not really the same as maximization of the nodes in the original RD-MIMO. Because here, as you can realize, we are maximizing the difference between those two rates rather than just maximizing the rate between the cluster heads, which is the RB of Q. So the maximization is different, and therefore the results of the selection of the nodes in your cluster that you will do, those nodes that you are going to select will be different for improving the secrecy rate as opposed to improving just the ergodic rate between the channels. I'm going to skip quite a bit here of those slides, just again in interest of time. The results that I want to present to you is what happens when the location of the eavesdropper changes. So here we have a scenario in which we have two clusters which are relatively far away relative to the dimension of the clusters, and we have Eve move in vertical upwards upwards motion, and we can see what happens as Eve moves across this line, what happens to the secrecy rate. It depends on the number of selected nodes, L. In general, the larger number of selected nodes is the better the secrecy rate is. However, as you can see, the secrecy rate has minimum when Eve is located at this location between the two clusters, which is closest to the transmitting clusters. This is, of course, clear. If I am Alice and I'm trying to design my system and I don't know where Eve will be located, where the eavesdropper will be located, then clearly I need to assume that Eve can be anywhere if this is the only possibility of the locations of Eve, and I'm going to choose the minimum of those curves as the possible secrecy rate. We can also see here the curve in which we have only the head nodes transmitting and the nearly vanishing secrecy rate when I do not use the distribution of the nodes. So I just use the head nodes to communicate directly. The secrecy rate is very low. I can improve significantly the secrecy rate by having the distribution of the nodes. Okay, a similar example holds for the case in which the cluster is much larger. Really what to see here is that due to the node dispersion, I can still continue to maintain significant secrecy rate even if Eve is relatively close to Alice. And this is due to the distribution of the cluster. Because I have so many nodes in my cluster that some of the nodes in my cluster, I can choose those so that they will serve as good channel of high quality channel to the destination cluster, where they will be relatively poor to the to Eve. Another aspect of this, and I will take another less than 5 minutes to finish. Another result is what happens with mobility. If I assume that I can delay my communication within some window of time. So in this case, that window of time, 10 seconds. Of course, you may claim that you don't want to wait 10 seconds to communicate, and I would agree with you. In real-time communications, that's probably not a very realistic assumption. But if the idea is to send some batch traffic, for example, or just for the purpose of presentation, if you can delay your communication over some window, over some period, and choose the base secrecy rate that occurs within this window, you can gain a lot by the fact that the nodes are going to reconfigure themselves within this period of time, and therefore, presumably over this period of time, there will be constellation that will give you high secrecy rate. So this is what happens when the mobility of nodes increases. This is increasing the mobility of nodes. The larger the mobility of nodes, you have more diverse constellation of nodes to choose from, and therefore your secrecy rate will increase. Okay, I'm going to skip the next few slides. I'm just going to very quickly mention a couple of other works that we have been doing related to this RD-MIMO technology. One has to do with artificial node injection in this RD technology world, in which I select a small number of nodes to artificially inject noise, and therefore presumably improve, with the intention to improve the channel between me and the destination much more than, or let's put it this way, hurting the channel between me and the eavesdropper at the expense of improving or much less hurting the channel between me and the destination. The scheme actually, by judicially selecting those nodes that inject the noise, can take a performance of the RD-MIMO, which attains a very low or relatively lower secrecy rate, can significantly improve the secrecy rate by taking those areas, geographical areas, so to speak, in the plane in which the secrecy rate is reduced. I apologize for this. Another work that we have been doing has to do with full-duplex transmission. If the destination can inject jamming signal at the same time that it receives the signal from the destination, in such a way that it can remove the signal from the jamming signal from the total signal that it receives from the destination, it's able to create or inject jamming into the eavesdropper and not inject jamming into its own reception. So full duplex communication has been, again, quite active area of research recently, and we have analyzed this for the case of the RD-MIMO under certain assumptions, and shown that it's extremely effective in improving the secrecy rate. Okay, the good news, we are at the last slide. Conclusion and some open questions. So we showed that mobility and the dispersion, geographical dispersion of nodes can significantly improve the system performance, both in terms of the ergodic rate of the system, as well as in terms of the secure rate between the clusters, between the nodes. Our analysis assume a practical model in which the RD-MIMO architecture, in the RD-MIMO architecture, the knowledge of the eavesdropper is unknown. Some results which I didn't have time to present to you, if you can somehow provide an exclusion zones for eavesdropper, you can significantly improve the performance of the scheme by limiting by assuming that the eavesdropper cannot be present in certain locations. So, for example, if I have, just as an example, if I have a building in which I know that only people that I trust are allowed in, I can create an exclusion zone around this building saying, I presume the eavesdropper will not be present in this building, and therefore I can significantly improve by this assumption, improve the minimum security rate and therefore the security rate of the system. The schemes that we discussed, or the approaches that we discussed to improve the efficiency of the secure spectral efficiency is through transmit node selection, leveraging the node mobility, especially in situations in which there's some delay tolerant in terms of using the channel, the MIMO channel, to transmit the information. We discussed very briefly distributed noise injection, determining of exclusion zone, and therefore the example I gave you, the building, and being able to determine that the eavesdropper cannot be there. And finally, very briefly, we talked about full duplex transmission. Some of the open questions which we are still considering how to approach them and to answer those is how to create the coding scheme for the general fading channel that will achieve the secrecy capacity, and designing of optimal pre-coding, which I didn't have time to talk in my to discuss in my talk, in terms of achieving again optimal capacity of the system. So this sort of concludes my talk. I appreciate you being so patient and listening through this long stream of information coming your way. If there are any brief questions, I will be delighted to answer. If you have any, you're always welcome to, of course, contact me through email. Any interest in collaboration of this and other topics always are welcome as well.
Thank you very much. So,
yes, sir.
I have a question. You assume that the eavesdropper has only a single antenna. What happens if you allow it to have the same capabilities as the receiver of a cluster?
Yes. So actually, some of the results, again, I didn't have time to go over those. The assumption was that eavesdropper does have multiple antennas. So M is the number of antennas of the eavesdropper. In the case of this graph, you have a small number of antennas and some performance where DE is the exclusion zone. And this is the number of antennas of the eavesdropper is much larger, not much larger, it's larger than the number of nodes in both of the clusters. And of course, the performance in this case is significantly lower than in the case of less powerful eavesdropper. So clearly, a more powerful eavesdropper allows you to achieve less secrecy. It comes at the expense. But the idea is that if you optimize it, even in those situations, you're able to achieve significant improvement. Yes, sir.
Okay. Thanks, Zygmunt, for a very interesting talk. I think you opened up a number of interesting ideas, and I have some more detailed radio engineering issues that we can bring up later. But I have a question of more principal character, and then maybe Panos can answer that as well, comment on that as well. Because if you now go to this information theoretic view, of course we know what the secrecy rate is. So in principle, if we have infinitely long codes, we could guarantee secrecy. But in practice, we have to go with shorter codes, and when we know how to design them, then we can only guarantee secrecy up to a certain probability, right? So this is the difference from the sort of cryptographic schemes, and I don't know if how sort of security community would react to that, to say that we can guarantee secrecy with 10 to the 6 or 10 to the 9. Right. Whereas the cryptographic environment, they rely on that the person or the eavesdropper doesn't have the code cracking capability, so that will take him so much time or so much effort.
Right. So you're absolutely right. You're absolutely right that the results of the physical layer security assume very long codes for the purpose to achieving this secrecy rate. And you're also, of course, very much right in stating that the security community likes a binary type of security. Either a system is secure or it's not secure. You don't say it's secure in 99.9%. I like it to be 100% secure. What I want, however, to say that even if you are able to provide me a very high degree of security, you mentioned 10 to the minus 6. Let's even make it more practical, 10 to the minus 3. If I use the system multiple times to convey a piece of information, then essentially I square or raise to the power of the number of times that I use the channel to be able to convey my information. So in other words, it's true that with each attempt of my transmission, I can only assure 10 to the minus 3 probability that the information will be conveyed secretly. But if I take my information and then divide it into multiple blocks, so to speak, and maybe encode it clearly for the purpose of making sure that if you get one code, one block, this is not enough for you to infer the whole message, so to speak. And I use the channel multiple times, especially over a period of time, then essentially I increase to the power of whatever the number of times that I use the channel is in terms of increasing the probability.
Okay, thank you.
I would also like to ask a little bit more with respect to the distributed MIMO part of your talk.
Yes, sir.
So if you compare, let's say, where we're standing from a information theoretical point of view with implementations that we see today. So where do you see the biggest obstacles in ripping off these theoretical results in practical deployments? Do you have any research on that or any insights?
I think that there's a difference between research done on academic institution and trying to convince the standard organizations and industrial partners of validity of certain approach. I think that the main obstacle is with people believing that this is a viable way to implement such systems, and truly that they will gain those insights. That the gains will be as indicated by the theoretical theoretical calculations, so to speak. I have been in my career working both for industry and academia, and I know that industry is looking at much shorter time to implement products and services than we are looking in academia at those problems. So really it takes some maturity of technology to be able to convince standardization bodies to look into certain architectures. I am a true believer that the collaboration among nodes will be eventually will make its way eventually to standardization of bodies such as 3GPP, for example. Maybe not in 5G, maybe in 6G, or maybe further down the line. But I think that it's such a powerful tool in being able to improve the capacity and improve the performance of the systems, that eventually the standardization bodies and industry will look into those technologies.
Unless there is no more question, I'd say let's thank Professor Haas again.
Thank you very much.